तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Okay, good morning. Today we start our discussion on a series of lectures titled High Speed Devices and Circuits. Okay. My name is K. N. Bhatt. I am from the Microelectronics section in the EE department at IIT Madras. The reference books, maybe I can hand it over to you later. You can just see one of the books that I will be referring constantly for material properties will be Saurabh Gandhi's, S.K. Gandhi's book on VLSI fabrication principles, second edition 1994. Then there is a book by Chang and Cat, gallium arsenide high speed devices, physics, technology and circuit applications. There is a book by Benecking, high speed semiconductor devices, circuit applications, circuit aspects and fundamental behavior. There are few things, it is a very thin book which contains some things which we do not usually see otherwise, which are relevant to high speed circuits. That is another book which we can just see. In fact, this book is available in library. I have a copy of these two books. I bought it specially for this course, but I do not know how much of it I will follow, but still we will have material from various literature borrowed here. The other books which are available in library, one is Michael Schur's book on gallium arsenide devices and circuits. It's slightly old book, 1987, but quite good enough for the basic studies. Then Zay's book, 1990, which I am sure you have seen in the library, high speed semiconductor devices. Lastly, there is one, the first time when I was seeing these areas, I saw a book on VLSI electronics, gallium arsenide microelectronics. This is also available in the reference section. Okay. So, these are some of the books which you can use as a reference book, but generally I will be giving you the summary or the gist of various details related to the gallium arsenide devices, high speed devices as well as circuits. There is a lot of emphasis on devices, but definitely circuit part also will touch upon. I will not highlight what the syllabus is going to be. In fact, if you go to the website, you will see the syllabus. High speed devices and circuits. When you say, you can immediately see that there are two classes of devices and circuits. One class based on the silicon devices, and when you say silicon devices, immediately you will see MOSFET and bipolar junction transistor circuits, BJT. Okay, that is very popular both in digital and analog circuits. Further classifications we will see later. Major device areas are these two. Okay. The other one that you will see will be the compound semiconductor devices. We will see why we should move from here to here for high speed during the course of our discussion. And when you deal with compound semiconductor devices, you will have MESFET, that is metal semiconductor field effect transistor, as against MOSFET in silicon integrated circuits, and also you will have high electron mobility transistors as against MOSFET and JFET, and the other one will be HBT, heterojunction bipolar transistors. which actually a replacement for the conventional bipolar transistor. Okay. Now, some of the circuit aspects also we will definitely touch upon. For example, some concepts of logic families involving this type of devices, which are different from those MOSFET based logic circuits. Okay. Let me not name them right now because there is no point. So, these are the general idea. Now, we will see silicon based circuits dominate the VLS applications. First, we will have to see why it is so dominating, why it is all pervasive. Next, we would like to see why should we look for other materials. Those are the two aspects we will just discuss now. So, you notice I just put it deliberately on the left hand side, so that some space may be required for here. There is a shifted everything to the left slightly. Now, silicon based devices or silicon is very omnipresent because of various reasons. Number one, you see it there, silicon is the most abundant material on the Earth's crust. It forms 0.238 weight fraction of Earth's crust. Okay. In fact, there is a joke on this. You can go to beach, collect some sand, that is silica, and you can reduce it to silicon. So, in plenty you have silica, that means in plenty you have silicon. That is one of the major reasons for why silicon is very popular. Now, apart from that, there are other reasons, like the chemical stability of silicon is extremely high. When we say chemical stability is high, what we mean is we can immerse silicon in at room temperature, particularly in all chemicals, acids, alkalis. For example, you can dip it in nitric acid, you can dip it in HCl, or even you can dip it in a combination of HCl, HNO3, that is aqua regia. So, even aqua regia, the most dreaded chemical which will eat or etch gold, will not affect silicon. That is what we mean by saying it is chemically very stable. It becomes very easy to process because you can dip it in various chemicals. Okay. So, that is one of the advantages, major advantages that silicon has compared to most of the other semiconductor materials. So, unless we require them very badly, we will not go in for other semiconductor materials. Silicon surface can be oxidized to silicon dioxide. This is another advantage. Okay. You just put silicon into, or just subject silicon to high temperature like 1000 degree centigrade, pass oxygen, you have immediately silicon plus oxygen will give you silicon dioxide. Temperatures that we talk of are 900 degree centigrade to maybe 1100 degree centigrade. That is the range. So, you can easily convert it. Either you can use oxygen or you can oxidize in a water vapor, H2O. Result is the same, silicon dioxide, silicon is converted to silicon dioxide. It is called the native oxide. Now, it has several uses. Why do you say if you oxidize silicon, so what? So, if you see the slide, you can see this silicon dioxide is used as gate dielectric. In a MOSFET, you have a gate and an oxide. The gate dielectric is very effective and very powerful with silicon dioxide. Metal oxide silicon, that is MOS structure. You can make with a metal, then the silicon dioxide, then silicon, that is MOS structure. So, now you also have other advantages like the masking and passivation. Let us just take a look one by one. So, one is the gate dielectric. Okay. SiO2 can act as gate dielectric, okay. And 2 is second one is the masking layer. This is like this. You have a silicon substrate, P type silicon. On that, you can have a thick oxide, okay, and then you have this that is a gate, and then you have the, I don't know whether it is visible, N plus. This is actually the basically the MOSFET structure, source, drain, a schematic representation. So, what we are trying to say is you will have this portion which is colored, that is actually the gate oxide, which already you know. I am just reiterating just to fill in whatever information required. This is metal oxide semiconductor. This is very effective as a gate dielectric. This is called gate dielectric. This is the field oxide. This portion. That also is silicon dioxide. Now, the advantage here is, second one is the masking layer. See, for example, when you do this N plus diffusions, you use this oxide as the mask, which will prevent the diffusion of dopants through that layer. So, the silicon dioxide is a very effective masking agent against impurities. Okay, that is what we are saying by implying when we say masking layer. And the third one is passivation. Notice here the junction is below the oxide. Okay. The junction is protected by means of this oxide. So, that is what we mean by saying the junction is passivated. It is otherwise it is very highly reactive. When you have the oxide on the junction, its reactivity is reduced on surface. So, contaminants do not go and reach the surface. So, it is a protection layer or a passivating layer. In layman's language, you can say it is a protective layer. In electronic terms, you can say it is a passivant. Okay. Those are the advantages that you have for silicon dioxide. In fact, this is the major advantage of using silicon, because you can convert it to oxide very easily. Other benefits of silicon in integrated circuits is the energy band gap. Okay. The gap between the conduction band and the valence band is 1.1 electron volts. In fact, what you mean is the energy gap 1.1 means it requires 1.1 electron volts energy to remove the electrons from the valence bond and make it available for conduction. Okay. So, that means sufficient amount of energy must be given to break the covalent bonds, to remove the electrons from the bond. Okay. What is the big advantage of this? For example, if you take germanium, this band gap is 0.72 electron volts. So, okay, that is one of the reasons why germanium lost its market compared to silicon. Okay. Because if the energy band gap is small, whole electron pairs can be created very easily. Okay. So, if you make a junction, if the temperature goes up to 60-70 degrees centigrade, the junction becomes very leaky, and if the junction becomes very leaky, it is no longer a effectively rectifying junction. Result is the transistors etc. do not work properly the way you want to work, the way you want them to behave, it does not happen. Okay. That is why that is one of the advantages. In fact, going back to the previous slide, previous advantage, silicon can be oxidized to get silicon dioxide, whereas germanium, you may ask, can't you oxidize it? you can oxidize germanium, you will get germanium dioxide, okay, or germanium trioxide, but that oxide is not chemically stable. When you process by dipping into chemicals, it will just get washed out very easily. Even the dilutest of dilute chemicals will etch out the germanium oxide. Whereas silicon dioxide, very highly stable chemically, just like silicon. The only chemical which will etch silicon dioxide is hydrofluoric acid. In fact, you should be able to etch with some chemical, so otherwise you can't handle it. At least there should be some boss who will control that, that is hydrofluoric acid. Okay. Germanium, of course, that way it is very weak, germanium oxide, it can get etched very easily. So, that is why, so on 2 counts, germanium lost its market. Though the transistor initially was invented germanium, within a decade silicon took over, because one is the advantage of high band gap 1.1 electron volts, 2 is the advantage of the oxide. Now, the other advantage that you see now, so this is I am just putting it as an advantage, in the sense, since silicon was made use of for realizing integrated circuits, the vendors who sell the wafers started growing bigger and bigger diameter wafers. In the sense, you grow a rod of silicon, then slice them to get wafers. Today you can grow 12-inch diameter rod, a rod which is 12-inch diameter. In fact, Intel etc. use only 12-inch diameter wafer by slicing them. In India, we have 4-inch diameter wafers, BL, Semiconductor Complex Chandigarh, 6-inch diameter wafers, ITA Bangalore, Sitar, they use 6-inch wafers. So, these are some of the companies. There are also companies which deal with compound semiconductors. We will come back to that later, because we will see whether we need them at all. In fact, there is one company in Hyderabad, Gatek, which entirely deals with gallium arsenide based devices or high speed devices, high speed integrated circuits, monolithic micro integrated circuits, MMIC. Okay, that is a reality, it is not a myth. So, now what we are seeing is we can grow 12-inch diameter wafers by using what is known as Czochralski technique. Okay, that is melt silicon from polycrystalline material, dip seed crystal, pull it to get that thing. This is, I am sure you have studied in your technology course initially. So, these are the things which have projected silicon into the forefront. Now, let us see what are the parameters which limit the high frequency performance or high speed performance of the devices. I think without telling anything, you will say the parameters which will kill the high speed operation of devices are resistors and capacitors, because wherever resistors are there, combined with the capacitors, you will have the RC, time constant delays will be there. It will affect the high frequency performance, it will also affect switching speeds, because wherever there are capacitors, you have to charge those capacitors, and if they are accompanied by the resistors, they have to be charged through those resistors. So, device routing, device capacitance and routing capacitance. Okay. You may have the integrated circuit where number of devices are there, but those devices must be connected from one to another by means of interconnecting leads or wires. In fact, that wire is not just connected like that, it is routed on the surface of the oxide. So, those wires will have capacitance to substrate, and those capacitance are called the routing capacitance, or you can pronounce it like routing capacitance, whichever way you like. Okay. So, it depends which part of the world you are talking. Okay. If you are talking in America, it is a routing capacitance. Other thing is device capacitance, like junction capacitance. Okay. And also, when you talk of MOSFET, the MOS gate itself has got that capacitance, that has got to be charged. Now, when it is getting charged from a preceding stage, it will preceding device will be driving these capacitors. When the preceding device is driving this capacitor, the resistance, the on resistance of the preceding device will come into picture, that is the R of the previous device. For example, CMOS, if you have the pull-up transistor, that will be the one which will be charging this next stage. Okay. So, that resistor is on resistance of the device. That on resistance is the one that I am referring to here. That should be kept low. Because if it is high, the RC time constant will be large. Okay. That is when you are using the digital circuits. Now, there are some aspects which are known as the characteristic frequencies. These are of course the parameter which control those frequencies really. Apart from that, there are defined certain frequencies which will be the figure of merit of the device. So, the characteristic frequencies of the devices particularly, or the circuit for that matter, one is the cutoff frequency related to power relationship. Okay. Cutoff frequency, that is, at low frequency you get certain power output from the device. Now, that power output will become 50%, okay, that is 3 dB point, 10 log half, 10 log half is minus 3 dB, correct. Logarithm to the base 10, 2 is actually 0.3, 0.3 and 10, 3 dB. So, the 3 dB frequency is called the cutoff frequency, where the power output falls 50%, 3 dB point. Okay. Now, that is one. That evidently will be governed by the RC time constants of the devices and circuits. Then you have the transit frequencies. In fact, this may be a slightly different term which is related to transit time. Okay. Sometimes we see people referring to the cutoff frequency and the transit frequency one and the same thing. They are different actually. Okay. The transit frequency is related to transit time, which is actually related to entirely to the device, and the cutoff frequency is related to not only device capacitances plus the series resistance or shunt resistances which come across that device. We will see that. So, what is cutoff frequency? We have already defined that. Cutoff frequency, that is at Fc. To define that Fc, the power out P naught at cutoff frequency is 50% of its low frequency value, which is the maximum power output that you get. Okay. And that is why Fc is 3 dB frequency, because at log P naught by Pm, okay, into 10, 10 log P naught by Pm is 10 log half, that is minus 3 dB. At Fc, 10 log P naught by Pm is equal to 10 log 0.5, is equal to minus 3 dB. Okay. So, that is the cutoff frequency of the device. Now, what is the frequency, transit time, transit frequency? Okay. So, the next thing that we see is the transit times, tau t. This is, I am sure, very familiar for those of you who have taken at least one course on devices. This is proprietary of the device. Okay. Transit time is, as the name itself indicates, it is actually the length divided by velocity of carriers. If there is a length L, for example, if you have the channel length here, this is actually the channel length. Okay. That is the channel length. So, the carriers get transported from the source to the drain through this length with the velocity v. The transit time is the time required for the carriers to move from the source to the drain through a path length of L. Okay. So, that is why that will be actually the length divided by the velocity, and the velocity would depend upon what is the transport mechanism. For example, if you take the base region of the transistor, there also you can talk of transit time. The mechanism by which the carriers are transported is not by drift, it is by diffusion. So, velocities are smaller compared to drift. So, length there is the base width divided by the velocity related to the diffusion, that will give the transit time. So, apparently that is related, or evidently that is related to the base width, and some parameter which governs the velocity. When it is drift, the mechanism or the parameter which governs the velocity is when it is drift, the velocity v is equal to mobility of the carriers into electric field. Okay. So, that is call it as mu n into electric field, where E is electric field, mu n is the mobility. Similarly, there is velocity and length is L, channel length. Similarly, in the bipolar transistor, the velocity is related to not mobility, but diffusion coefficient, because the diffusion process is the driving force. Driving force is the concentration gradient. Okay. The force is dn into d by dfx, dn by dfx, where d is the diffusion coefficient, dn by dx is the concentration gradient. Here it is mu n into the driving force is the electric field. There diffusion coefficient into driving force is the concentration gradient. So, it is a diffusion coefficient. Diffusion coefficient also is related to mobility. So, what you can see is now the velocity of the carriers, whether it is by drift or by diffusion, it is proportional to, it depends upon mu n or another parameter which is related to mu n, that is diffusion coefficient. Because you know that dn by dn is kT by q, that is Einstein's relationship. Okay. dn is diffusion coefficient. Okay. Driving force in this case is diffusion coefficient into dn by dfx, concentration gradient. These are of course basic things which I am just reiterating. Okay. Now, let us go back and see what is this transit frequency. Okay. Tau t is length and velocity. Now, let us just find out what happens here. Let me just go through a quick derivation of that. How much is transit time and how is it related to the term known as the transit frequency. So, okay, transit frequency is defined. What it is we will see afterwards, physically meaning. It is defined as f t equals 1 by 2 pi tau t, where tau t is the transit time. Tau t is the transit time. Okay. Now, let us find out what is the transit time. This is a definition. Okay. What it implies when you really see the equivalent circuit, we will see soon. Sometimes we make the mistake of calling this as the cutoff frequency itself. It is the ideal cutoff frequency. So, tau t is length divided by velocity, that is L divided by velocity. Okay. Now, in the MOSFET, we will define this with respect to the MOSFET. In a MOSFET, metal oxide filled by transistor, V is equal to mu n into E. E along the channel, electric field along the channel length, source to drain. So, that is actually equal to mu n into What is the electric field in along the channel? Voltage drop across the channel divided by length, and voltage drop across the channel once it has in the linear region is just VDS, but once it goes to saturation, the voltage drop is VGS minus threshold voltage. It is VGS minus VTN divided by L. That is the electric field. Voltage by voltage across the channel divided by the length of the channel. That is the electric field, average electric field. Okay. Now, in fact, what I would do is I will write it one step. Un into VDS divided by L, which is actually equal to Un into VGS minus VTN divided by L in when you have to when ID is saturated. ID in saturation. Okay. So, anyway, ID saturation gives you that. So, now what is this actually? So, tau t transit time tau t is equal to L divided by V is L divided by V, which is actually equal to L squared divided by L divided by L squared divided by mu into VGS minus VTN. Okay. Here VTN is actually VGS source voltage, VTN threshold voltage. So, those are the well known definitions. So, just I did not mention that initially, but for sake of completeness, that is that. So, the transit time actually is this number. Okay. Now, let us just take a look at the transit frequency. If I use this as the transit time, what is the transit frequency? Transit frequency. F t, okay, is 1 by 2 by tau t. Therefore, omega t, which is actually 2 pi f t, is 1 by tau t. Please note that is the definition. Okay. That turns out to be then from here, from 1. From this equation, we get this as okay. That is the transit frequency. Now, let us do slight manipulation. Yes, finally, what we want to see is how this will be related to some of the circuit parameters which we talk of. Okay, because a circuit engineer may not like to say mobility, threshold voltage, all sorts of things. He may not like to analyze. So, let us see how it works. I will remove this now. Notice that what the transit time depends upon: channel length and the mobility mainly. Okay. I can rewrite this as multiplied by C oxide C oxide is the well known term gate oxide capacitance per unit area. Okay. So many farads per centimeter square. In fact, the value is about 35 nanofarads per centimeter square if oxide thickness is 100 nanometers, that is 1000 angstroms. If it is 1000 angstroms, then that is 35 nanofarads per centimeter square. Okay, I multiplied that and then I multiply by W into VGS minus VTN. I just multiplied by these two and then I divide by that. Okay. So, why did I do that? So, this I can write it as mu n C oxide W into VGS minus VTN divided by L, just pulling it out, and then I will write it as, I will write this as L into W into C oxide. So, here we should know what are the various terminologies. Okay, let us just see that, because in case you were using different symbols. Mobility of electrons, oxide capacitance per unit area of the gate looking from the top, W is the channel width. When I take the MOSFET, okay, I just unfortunately rubbed off that. When I have the MOSFET, it has a depth and channel length. So, channel length is L, W is the channel width MOSFET, and gate source voltage, threshold voltage. What is this quantity? L into W is the area of the gate, and C oxide is the capacitance per unit area. So, L into W is total gate capacitance. We can call it as input capacitance. So, this is actually equal to, so L W into C oxide is gate capacitance, total gate capacitance. I squared C I, input capacitance. You can call it C G or C I, just call it input capacitance. Okay. What is this quantity? In terms of transconductance, if you take. Okay. Let me remove these portions, top portions. I can remove it so that I can write from there. Okay. Okay, I will have some space here. I D in saturation for MOSFET is mu n C oxide W divided by 2L into standard square law, simplified version of this MOSFET characteristics, that is that square law. Okay. Now, let me remove this from here. Therefore, GM, what is GM? Transconductance is equal to delta ID by delta VGS will be equal to, differentiate that, minus so now you can see what is the that omega t is. Omega t we defined it as 1 over tau t, and we have finally come up to this, and this portion we know it is equal to C I, the gate capacitance or input capacitance, and this portion is nothing but G M. So, this is actually equal to in many places you will see that the figure of merit of the transistor is G M divided by the input capacitance. In fact, you can show, I will leave it to you for show as a homework, for a bipolar transistor also, if you define the transit frequency as 1 by tau t, that omega t will be equal to Gm by Ci. That is why I put Ci to keep a general term. In the case of transistor common emitter configuration, it is the capacitance, diffusion capacitance between the base and the emitter. Gm divided by the capacitance, that will be the cutoff frequency, or not cutoff frequency, the transit frequency, which will be actually be 1 by tau t. Okay? So, that is why I just kept it as Ci, not Cg, to keep it general. What is Gm in the case of a bipolar transistor? It is Vt by Ic is R, Ic by Vt is the transconductance. Collector current divided by thermal voltage KT by Q. So, if you have 1 milliampere current flowing, Vt, that is KT by Q, is 25 millivolts. So, 1 by 25, that is 40 milliampere per volt. That is the transconductance for a bipolar. Here you can see it depends upon this quantity. I can have better and better value of that by if I have better value of the Gm, okay, better value of Gm and smaller value of the gate capacitance. Okay, these are some of the guidelines which are being used. Okay, Gm can be improved by increasing W, but that is affecting capacitance also. So, by increasing the area, you will have the driving capability improved, but the capacitance also goes up. That is not the way to improve the speed of the device. So, you can't make it W, but you can make, if you make L smaller, Gm goes up, capacitance goes down. So, the way to increase the speed is reduce the channel length. Okay? It's without affecting the capacitance, you are increasing the speed of the device. This is one of the key things. More importantly, you can improve the speed of the device by if you can improve the mobility. Okay? And how do you improve the mobility? For a given material, you are stuck with the mobility, but mobility is better if the doping concentrations are low. But if you go to doping levels of 10 to the power of 17 of that level, the mobility will start falling. So, you must be guarded in the conventional applications not to go to very high doping levels. You must remain at the low doping levels. It has its own repercussions, we will see as we go on. Okay. You need to go to higher doping concentrations in certain cases. Okay. So, one way is to change over this material which has better mobility or better velocity. Okay, now, let us just take a look at the other aspect what we are telling. What is this cutoff frequency? Okay. How is it different from this transit frequency? Let us see that. Stop me if something is not very clear. So, I hope symbols are clear enough. So, Gm by C is a figure of merit, remember. This not only the device people will talk, circuit people will also talk. I am sure Professor Radhakrishnan would have mentioned this Gm by C. Okay. So, that is the transit frequency, which is omega t with 1 by tau t. Now, let us see the cutoff frequency. See, the transit frequency is totally dependent on the transit time, totally dependent on the device structure, okay, and the transport mechanism, because that decides the velocity. Now, for this we will see the MOSFET. Example, we will take MOSFET. Transit frequency of MOSFET, equivalent circuit. Equivalent circuit, gate, and then you have some resistor which may be the resistance of the gate region itself, and also the contact resistance. So, that comes up to the point, and then you have a capacitor. That is the gate capacitance C I which we are talking of. C I is the total gate capacitance which is equal to W into L into C oxide. This is R is the gate resistance. It could be also an external resistance if you call this as the G. So, okay. So, this is the input point. Now, if this is V I, after all we are talking of the small signal equivalent circuit now. So, which would mean that when I apply AC signal, there will be AC signal appearing across the gate capacitance. How much? The whole thing will appear here if this is 0, but it will never be 0. Some finite resistance, contact resistance, or the external applied resistance will be there from the supply. Then what is the other equivalent circuit? This is actually the source point. From then on, Gm times that voltage Vi, that is the equivalent circuit, because input you see from the RC resistance and capacitance, from the output point it is generating a voltage or giving a current source, the drain current, which is Gm times the gate voltage. So, that is current is like that, that is IL. I can put it as like that RL. You get the output there. Now, the question is, what is the IL equals? Let me just write it down. IL is Gm times Vi, which is actually equal to Gm times Vg divided by correct. So, that is the IL. Now, what we were telling is the cutoff frequency is the frequency at which power output becomes half. Power output is I squared L into R L. When the power output becomes half, IL becomes root 2 times. At Fc, P naught is half of Pm. Pm is low frequency maximum power. That is, therefore, which is equal to half IL squared into no. So, then IL will be 1 by root 2 times low frequency value. Is it readable? I hope it is readable. IL at Fc becomes 1 by root 2 times, because square root of that, the low frequency value. Okay. So, what you, so that becomes 1 by root 2 of low frequency value is Gm times Vg, because this impedance will be large compared to that, entire voltage will be across that. Low frequency value omega 0, that is that Gm times Vg. So, it becomes 1 by root 2 of that, then this becomes equal to 1. So, at omega c, okay, at omega c, omega r c I equal to 1, correct. Without even going through this, you would have said the cutoff frequency is related RC combination. Okay. I just went through that thing to keep the whole discussion open. So, now let us just go back here. Okay, I will remove this thing now. So, you have got the F c is 1 by 2 pi R c I. Okay. Is it all right? F c is 1 by 2 pi root R c. So, you can see the whole thing depends upon this RC combination, this cutoff frequency, okay. But the transit time cutoff frequency would depend upon Gm by C. Now, from this circuit point of view, can you tell us what will be the condition for omega t here from this circuit? You can see that cutoff frequency depends upon R and C here. Okay. Now, if you go on reducing R, it looks as if the cutoff frequency becomes equal to infinite. It will not, because this is now limited by this RC combination, capacitance input and the resistance of the circuit. But as you keep on reducing the R, what is the ultimate limit for the speed? Transit time. So, can you see what happens there? What is that Gm by Ci will be? Okay. That is what I try to illustrate. I want to bring it down to you here. Okay. That is, if you call this as I input, okay. Last thing on today, this aspect. I L divided by I in, how much is that? I L is Gm times Vi. Okay. So, Vi is actually equal to, I am sorry, I L is that, just 1 minute, I L is Gm times Vi. I can write Vi is I in into, if you have a current coming in here, what will be the Vi? I into impedance, that is divided by j omega Ci. So, I L is equal to Gm into I in divided by j omega Ci. Please, I am getting at something which we usually do not see. So, therefore, I L divided by I in is what? Magnitude, if you see, Gm divided by omega Ci. Now, you can see, okay, when omega is low, that is something. Okay. Now, I L divided by I in equal to 1, when this current here is same as the current here. Okay, gives what? That will give me, rewrite that, when I L divided by I in equal to 1, we get Gm divided by omega Ci equal to 1. Now, what is omega? Then omega equals okay, that is the key thing that I want to tell. So, when I L become by I is equal to in is equal to 1, the frequency that happens at a frequency equal to Gm by Ci. What is that actually? That is omega t. So, you have got now what we have done now is the transit frequency omega t is the frequency at which the current output is equal to the current input. That means, it is no longer working as the way you want to work. You can put the resistance here or as well as here. If you have a current that is pumped in, you get certain voltage output, I input into RL. Okay. Now, if this current is same as that, when I put it here, what is the output voltage that you get? IL is equal to I in, that also is I in into RL. You do not get any benefit of using that amplifier there, that circuit there.